rotation. Another very useful transformation in computer graphics is rotation. So before we saw how we can scale our objects, make them bigger or smaller, but we also want to rotate them, so make them turn around some axis. So the example of that would be here. So we again have the same geometry, the same square, and this transformation kind of rotates it. So in 2D, you can imagine it kind of rotates around the third basis. So if you imagine this like an XY plane in 3D, then rotation would be around the Z-axis. And you can see the matrix becomes quite messy here. So where do those numbers come from? Let's try to derive this rotation matrix. So we want to keep the basis vectors, the transformed basis vectors, on this unit circle. So here imagine we have these standard basis vectors. So E0 is over here, this is our standard X. And we have our E1, our standard Y basis vector. And we now want to move that basis around, well, axis Z, if you will, so that they stay on the unit circle and the angle between them stays 90 degrees. So let's imagine we have rotated them by this angle alpha. Now the next trick is we want to find out what are the coordinates of these standard transformed standard basis vectors. So for example, the coordinates of this E'0, because the coordinates of those transformed vectors will be the columns of the rotation matrix. Now to find these coordinates, we can kind of imagine this triangle here. So the x coordinate of this transformed standard basis vector would be somewhere here, and the y coordinate would be up here. This is how coordinates work, right? But these triangles actually give us a way to calculate these coordinates. For example, if you remember from your high school, how is cosine of an angle defined? So we have an angle alpha here by which we rotate it, and the cosine of that angle will be the adjacent leg divided by the hypotenuse, or rather the length of the adjacent leg divided by the length of the hypotenuse. Now this length here, this is our x coordinate. We don't know this length yet, but we know that this one, this a, divided by the length of the transformed basis vector, the hypotenuse, this is going to be cosine of this angle. And it turns out, because we started from the standard basis, the length was 1 of the standard x basis vector, and we rotated it along a unit circle, so its length stayed the same. The transformed basis vector still has length 1. We didn't make it larger or smaller. So this length of E0', well, this is just 1. And well, a divided by 1 gives us a. So we find out that the x coordinate of this vector is the cosine of the angle by which we rotated the basis. So the first coordinate of this transformed basis vector is just cosine alpha. Very similarly, we can find out the y coordinate. So sine of alpha is the opposite leg divided by the hypotenuse. So b divided by the length of the transformed basis vector, which is 1, will just give us b. So the y coordinate of this vector here, this is just sine of alpha. And now we have our first column in this rotation matrix. It's cosine alpha, sine alpha. And now you can see why the rotation matrix we saw before when we had this example where we rotated a square, the numbers became kind of non-obvious. So they're cosines and sines of the angle that we rotated. Now a very similar thing happens with the second basis vector, except that when we calculate the x coordinate here, the sine of alpha is actually just the length of this leg. But because the second basis vector rotated to the negative x-axis, we want to take the negative length, minus b here, because its coordinate, the coordinate of this vector is minus b, and the length of this is b. So the top right value in this matrix, the first coordinate of the second transformed basis vector, is minus sine of alpha. But the y is still positive, so y is just a cosine alpha, and the last value in the matrix is thus cosine alpha. And this is our rotation matrix. Cosine alpha, sine alpha in the first column, and minus sine alpha, cosine alpha in the second column. And this rotates in 2D around this imaginary z angle by angle alpha. And it's positive rotation, so if you have a right-handed coordinate system, then it goes counterclockwise in respect to alpha. Now in 3D things become a bit more complicated, so we can construct similar matrices that rotate around each of the basis vectors. So we can imagine this 2D rotation already as being a rotation around the z-axis in 3D, and we can use a similar construction to create matrices around an x-axis or a y-axis. But in reality we want to rotate around an arbitrary axis. And this is where there are more complicated techniques. In the material you can learn about like the Rodriguez's rotation formula or the axis angle rotation formula. So very often when you're working with different libraries that have vector math, you have this axis angle rotation function in which you give an axis of rotation as a vector and an angle alpha by which to rotate around that vector. And another way is this quaternion rotation. So it's a bit complicated, you can still read about it in the materials, but very often you have these quaternions, which are these 4-dimensional mathematical objects, which extend the complex numbers. And by doing very careful multiplication with these, you're also able to rotate around an arbitrary axis. And if you read more about these quaternions, they also allow you to interpolate between different orientations in the shortest or most optimal way. So they're really powerful, but they're a bit more complicated to understand right now. So from this video, you should remember the rotation transformation. So this rotates in the positive angular direction around a basis vector. And you should remember the derivation of the matrix in 2D. And notice that we use the fact that the columns of the transformation matrix are the coordinates of the transformed standard basis. So this is how we derive this matrix. So whenever you forget this matrix, you can just draw this rotated basis, check the coordinates, draw those two triangles, and see what is cosine alpha, what is sine alpha, and well, one is minus sine alpha as well. And you should also now know of other approaches for 3D rotations like the axis angle formula and quaternions, which you can read about later, but you should just know that these things exist.